All right. So at the end of last stream, I talked about symmetries, right? I was like kind of blabbering on about like execute episode, but I do want to mention that in the search, like we have to leverage the symmetries, right? Like this whole thing right here. So that's what I. So like today's stream might be really short. I'll just like my plan is to just like just like I remember like in the whiteboard, right? In this whiteboard, I drew like some like s like takes a state in the policy and then like converts it to s prime and like the policy prime, which is like the flipped about the vertical axis. And then in connect 4, you don't need to flip around the horizontal axis because like there's gravity, like it pulls it down like here, like we do, like we flip about the vertical axis. That means like the coin on 0, like the left coins, like this kind of L-shaped structure is generally on the kind of like the left of the state, and after the flip it goes to right of the state, right? But like top down, like if you flip about the horizontal, the other flip, like what's in the top becomes the bottom. Like that flip doesn't work for Connect 4 because of gravity, I guess, just because of the way the game is designed, right? But like if there wasn't gravity, if the coins didn't fall, then yes, we'd have to also take into account the vertical flips too. Like in BumperCoins, there'll be at least 4 different like flips, like flip vertically, flip horizontally, flip, and then like I guess a composite, like horizontal slash vertical, and then vertical horizontal. I think they might be the same thing. I'm not sure, but like they'll be like at least like I don't know, like flip that. Uh, I mean, there'll be at least like there'll be another vertical, like there'll be different dimension of flipping for bumper coins. So like I guess in Connect 4, this is the only type of flip. I mean, I'm not sure if there's more, like because of like the whole gravity stuff. I mean, but anyways, the point is that like that's what I need to do, like handle the symmetries. Like if you actually like look in the paper, like for like symmetry, like when the MCTS leaf node, the current neural network is called the reflected or rotated. Oh yeah, for rotated, I guess like Othello, like whatever is like 6 by 6 or like something. But the point is like they have a square board, right? Whereas Connect 4 and Bumper Coins is not a square board. So like if we transpose it like 7 by 6, 6 by 7, like it doesn't match up, right? So I guess there's only one reflection we can do, which is reflecting about the vertical, like a midline, the prime meridian, so to speak, right? So we call the neural network with the reflected rotated version. So like we flip a coin if it's like heads or tails, like kind of like that. Whereas in bumper coins, it's like kind of more combinations. In general, we started, and not only this, like this is not the only thing. If you read the paper, like there's another detail too about symmetry, and that is that when we're training, I mentioned this last time, when we're training our neural network, right? Like when we like do this line right here, we train it on the examples. We also take the examples and we use the symmetries to generate more training examples. So like symmetries are used, at least to my understanding, in 2 points. One here, this train function must like kind of do a data expansion, like take the examples and then like kind of double them, quadruple them, 8 times them based on how much symmetries we can exploit, how much symmetries we can use, right? So that's then the other thing is in the search function, like like in our create node function, which is kind of the analogous of this line right here, it's not just predictive S, right? But rather we kind of use symmetry. Like we could use symmetry and like do S prime here. Like we flip a coin, whatever. We randomly choose like some transformation of S, right? I know I said the word random somewhere or reflected rotated, but like we kind of, I mean, I think you just like randomly do it. But the point is that like this whole logic right here, we need to implement. So let's do that. And I can kind of be cute and just do an identity function too. So okay, yeah, let's get started. Let's see where I'm at. Okay, so what is this file? This is mcts.ts. Okay, let's quit out of this. Get status. Everything's clean. Get pull just to make sure that like, I like to do this. Already up to date. Okay, good. Get log. mcts search. Untested. I remember talking about the comma untested stuff. Look at our commits. Untested. That's what I did yesterday. Yesterday I did very little. I guess I did lots of talking. I don't know what I did yesterday. The day before yesterday, like my 2-hour stream, that's when I did a ton of work right here. Here was quite little, I guess. Yeah. Refresh, make sure, yep, everything checks out. It's the last commit. Alright, so let's get started. Let's create a new class called, let's cp, let's say move.ts, like the canonical TypeScript file into let's call it symmetry. How you spell symmetry? Symmetry, okay, 2 M's. I was gonna get it, obvious. Symmetry.ts. Okay. Get status. It's an untracked file. Let's do some work on it. Let's call this class symmetry. Okay. All right, now time to do some considerations. So like symmetry, right? Like what, like I don't think it has any like actual data in it. It's just like the or no, it does. I guess a bunch of lambdas, right? A bunch of lambdas. Status at all. Wait, no, not at all. Status, no, whatever. Okay, so then like the point is that like we need like this arrow, and then this other arrow going back, right? Because like, well, when we train it, like we have like SP, like let's call this like, when we're training, right? When I say train, I'm referring to this function right here, train net for the examples, right? Like let's say that we have like a training example S, this, like the state, the game state, the policy vector, and the reward, I guess kind of X, let's call it R. And then we're also going to train S prime, P prime, and R. Right? So this is like, if like that's kind of like one training sample here, or this is the P, and then like kind of we also have to pass in like this other piece. So like we need to know how to transform this. We need to know how to transform that. And then yeah. And also when we're actually like, doing the multi-color tree search in the leaf node, right? Like when like this is like kind of like the base case, like the leaf node case, when I'm calling create node my function, we're doing this. What we have to do is the policy we get is actually P prime, right? Like we have this S and we flip a coin. If it's tails, we just kind of take the happy path. But if it's heads, then like we kind of like flip it and then we call the network on this. We got some value, whatever, that's fine. And we get a flipped policy. So we need to like recover it. So like we have to inverse it. So like we need like we need to like this PFS is actually P prime. We need to go backwards to restore the actual P, right? Like if this is like the state and we want this policy, right? We flip it and we get this policy. We have to flip back to recover this policy, like P prime to P. So like we need those 3 arrows. Like that's our 3 functions. Okay, so let's kind of like let's give it some names, right? Let's put after constructor, obviously. Yeah, how do you do a function in TypeScript? Let me just right quit that and then open gamestate.ts. Gamestate.ts. Okay, great. Let's see how they do. Okay, so that's kind of one example, right? Let's copy that line here. Let's paste it. I'm kind of hungry. I want to grab lunch, so I want to like do something quickly. So get game state. So instead, what we need to do is we need to return the game state, right? Game state. The symmetry takes in a game state, which is sorry. So it takes in a game state and returns a new game state. Let's call this like kind of a linear map, a linear like a transformation, transform game state goes from S to S prime. And let's kind of copy these three. Let's copy that. Goes, and we're doing the same thing for policy, right? That is never mind. Goes from P to P prime, so this will be transform policy, right? Policy. Okay, so transform policy. And then, so like this will be the first arrow, second arrow. So that'll be this. This will be that. And we need the reverse, right? So let's call this transform, like, I'm thinking kind of like TFS, right? TFP. And then I guess like mathematically it'll be kind of like T inverse of P. Should I call it inverse transformation? Like, should I kind of like have like inverse here and like that? Or should I have, I think what I feel like doing is kind of sticking it there. Just so all the method names start with the word transform. Should like kind of like, it's not like it's like T transform then inverse. Inverse, yeah, let's do transform inverse policy goes from P prime to P. Okay. And then each symmetry has its own way of actually doing that, right? So those will be like the what do you call that? These variables here, these members. So TypeScript function member, like a lambda. What's the type of function? Okay, so like this. Fn for function. I remember when we saw like comparators, like when I was like doing the comparator for sorting the policy, that instead of like the word comparator, it had something called a compare fn. So I guess fn is like the JavaScript convention maybe for lambdas. Okay, so something like this. Let's just copy that for reference. Paste it here. So then like this signature is like it takes in a game state, right? Well, we can just call it RS. Sorry about that. Let's kind of take this here. Go there. I'll have to do the imports too. Let's just do that later. And this will be copy this name. Transform game state function. And then we finally need a transform inverse policy and an fn, obviously. Don't forget the fn's. Inverse policy. So that policy, so these three things look good. Now let's kind of pass them in the constructor, right? So then this thing right here. Oh, we need the bracket. I mean, we need the semicolon at the end, right? Okay, that looks good. Now let's actually let's do it. Let's kind of put that in the constructor. And let's pass that there too. Three parameters, right? Okay, so does this look good? So we have a transform, we have like a lambda inside. Transform game state function. Oh, why is it doing, okay, whatever else I have to do from there. We have this, the transform game state function, which its type is a function that takes in game state, returns game state. Same thing for transform policy, swap the game states for policies. Let's call this P, and let's call that P. Because, like, I mean, yeah, we can kind of, it doesn't really matter. It's just, the whole point is that, like, it takes in a game state, policy, 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 policy. Like, just the types matter, not the actual, like, whatever name. We can pass in any name we want. So, like, that's not really, let's keep it as terse, as concise as possible. Okay. And then like, these are, like, our three lambdas. And the constructor will take them in. So transform game state function, the same exact thing I copied, just like the lambda, lambda, lambda. We pass it in, and then now it's time to actually invoke them. So let's do that. Return this dot transform game state function applied to the game state. Game state. Let's copy that there. Well, no, let's not do that. Or wait, no, yeah, paste. And this dot transform policy function. And then do it on the policy, obviously. And then finally, transform inverse policy, kind of same thing as that, except the word inverse in it. Right. And there we go. That is our symmetry. Okay. Okay, so let's create our symmetries, right? Like here, there's like two cases. Either like, oh wait, let's close that board. Either this or this. So this, let's call this the identity transformation. I mean, I'm not sure it's necessary, but I just kind of feel like it's nice to have. And then let's call this like mirror or flip horizontally. Flip horizontally. Okay, yeah, so let's kind of like, let's create those symmetries. I think we have to export them. TypeScript export. Modules export. Yeah, something like that. Export symmetries. How do I spell symmetries? Symmetries. Export symmetries, which is an array of symmetry. And let's call this identity, and flip horizontally. Okay, save that. Again, I've not actually defined these, so let's do that. Add some space. Let, or const, I guess. Actually, I've never used const so far. I don't really know. I just saw these guys use it, and I thought that'd be cool. Anyways, const identity equals new symmetry okay. So then this function is a what? Actually, for now, let's for now, let's just only do identity. I just want to see if it compiles. I'm not sure. I remember like one time this arrow sign caused some issues with compilation, I think. When I was like doing I remember like there's some issue with that. So I wanted to make sure we can actually pass in the lambdas. For now, let's do identity. So identity, it takes in three things. First thing is a state that returns a state, right? Should it like, does it like mutate it, or does it like return a new one? I think it should be like immutable, right? GameState.clone, we can just pass that in, right? State.clone. No, it's not static. So then it would be called GS. Function that takes in the GS and returns gs.clone. And then for policy, what we need is do we have a way to clone policy? Well, policy is actually never like, it's never same with GS. It's not actually mutated. Like we never actually mutate it. We just kind of like, it's a read-only thing, not a write. So yeah, let's just take in the GS and just kind of return the GS. Really simple, right? Same thing here for policy. And then the flip, and same thing here, right? Very elementary symmetry that we passed. Now we need to import things. Import move. So what we need to import is the game state. We need to import the policy. I think that's all right. And is this it? Game state policy? That's all? Well, for now, we're gonna obviously, we obviously need the move later too, when we're doing like the flip, right? The move is baked in a policy. Okay, let's see if that compiles. Okay, there is some problem. Oh, we caught a bug. Yay, type system. TS line 11. game state function, policy function, inverse policy function, inverse policy function. Okay, checks out. What's the other error? Const symmetry. Oh, it's an array of symmetry. Wait, I thought I'd, wait, what? Did I not do that? Apparently not. Clear. SH. Actually, there's no need. Wait, good, it compiles. I'm glad to see that. Get status. Get at all. Get status. Okay. So then, actually, let's just look at our .run.sh file again. Run.sh. Let's just copy this, because we only need to copy that. Like, we're only doing it server side, right? So what we can do is like that file for this for now. Okay, yeah, okay, let me just like kind of save that file. Okay, good. Get status. Get status. Because like there's actually no need to like do the whole browser file, like kind of, you know, like stitch all these JS to like bundle it all into like one min.js. And there's no need to start a server because like this front end stuff is already done. Now what's just left is training our network. So this is all back-end work. New file symmetry. Good, good. That looks correct. It compiles. And then let's do the fun part, right? Let's do the fun part. Which is delete or go here, right? Let's copy that at the end. Paste it. Delete. So now like what we need to do, oh, we have to give let's call this a symmetry. Good. And then what we need to do here is to paste a new one and call this flip horizontally. Okay, so now what we need is to actually like create it, right? Let's call this let's a function let or const flip game state horizontally, which is a function that like this. Like that, right? Well, obviously we need to actually define it. Equals function JS game state returns a game state. Okay. For now, let's just return game state just to make sure it compiles. I'm just making sure that it compiles for now. I will actually implement this shortly, very soon. Okay, I want to see this compiles. Good, compiles. Great, that looks good. I want to just break it to make sure it doesn't compile, just to like kind of verify that there's an error here. Oh, okay, that's bad. Let's like return 1, a number, not a game state. Number, not assignable type game state. Okay, I just wanted to make sure that this command does what I wanted to do. Okay, let's again now let's actually implement this. Okay, so first what we should do is clone the game state, right? Let's clone it. Or no, let's actually look at how clone is implemented, right? It's very similar to clone. Okay. Okay, so we have to like. Okay, so now let's call this flipped game state. We want to return our flipped game state, right? Pretty straightforward there. First, we have to copy the game state's turn. Actually, I want to do gs.clone. Let me just .clone it. I just want to. I'm not cloning the policy, but I just want to clone it just to create a new object. Just I don't know. I just feel like it's not such a big deal. It's not a huge deal. I hope. Maybe I should make a policy clone too. Actually, I'll just put that in the back burner for now. Okay. So flipped game state, right? It will create a new game state, and then P1 turn, copy that, and now, again, I could have like just done used whatever, like kind of like this, right? So now, rather than like just kind of doing this dot cells, what we need to do, so if we have a row R, column C, right? Then okay, so this is like let's just take this for example right here, right? This is what? No, let's not do that one. Let's do this one right here. Actually no, let's just do this one right here, right? Let's call this let's say this is R comma C, right? At R comma C. Then where does this end up, right? This ends up at what? Well, the R is clearly the same, just visually speaking. Like the row, like vertically, like is still the same. The R is unchanged. But then the C, I think I derived the formula right here, right? C would be the number of columns, calls minus 1 for the 0 index, and then minus C, right? So like, if it were 0, if C were 0, right, that means this thing would just be columns minus 1, which is the last column, right? Size n, and minus 1 is the last thing based on 0 index. Good. So then, as we populate this, like when we're kind of iterating, when RC equals like 4 and then whatever R, then we source it from the same R, but then we do that for the C, right? I remember it's kind of like a matrix. I know like something about like kind of transforms of graphs or something. Like there's like one column interpretation, one row interpretation, where one way of thinking is like kind of column wise, which is like row wise, which is kind of like for each cell in the destination, like how does it come about? Like for each cell in our answer, it's like kind of two interpretations. One interpretation is like, for a destination, how is the source transformed to arrive in the destination? And then the other kind of dual view is like, for the sources, how are they transformed? Like where they end up? Like, is it source to destination, left to right, or like right to left? It's like, they're the same. They work out to be equivalent notions. I'm kind of looking at destination, like looking at which source to take. But regardless, this formula is really nice, so we just kind of plug it in, right? So now, what do we do at the RC thing? Like, what cell do we take? Well, we take in this game state, right? This game state GS, and then we take GS dot cells. The row is the same, but then this thing changes, right? Specifically, it becomes static game state dot num calls. The game state dot num calls -1 minus c. Does that look correct? Game state, row is the same. Num calls -1. Okay, let's just say what happens when 0, 0, right? So when it's 0, 0, then game state dot cells, we take the 0th row, and then we take C0 like this thing here. So when we're working on 0, 0 for our destination, right here, then what we get is 0, like we get this right here. So like basically like if we have like this thing here in S, then this cell in S, when we're getting S prime, like when like the game state that we return, the flipped game state, which is S prime, like this thing right here would come here, right? Like, and if you like kind of draw the dotted line, and like we fold it, like we fold everything like there, like everything kind of folds itself, then like, yeah, these get swapped. So that is correct. The R is a change and everything gets swapped. All right, that is quite self-explanatory. Yep, it's like the classic interview question, like very basic, leak code easy, trivial, like just how do you reverse a string, right? It's kind of like you just like kind of like do it in terms of like pairs that get swapped. Like you just keep doing it. Like you can do a 2-pointer approach. Just like kind of just like keep swapping, and then yeah, like these are kind of like a complements, and that's like the function that like kind of gives you the complement size, like the size -1, and then like the minus the I for reversing. Kind of similar concept, right? I think I'm done. I think that's all for symmetries, right? Well, no, we have to do the policy too. So now, like, we have to replace that. So something similar to this, right? And again, let's just stub it out. Return P. So this thing is going to be called flip policy horizontally. And I believe that like in the case of connect 4, going from here to here and from here to here are the same exact things. They're the same. So I think that in this case, we just kind of flip the policy horizontally, and that's it. The policy, so it takes in a P, which is a policy, and it returns a policy, and then P. I could just copy the whole thing, actually. No, whatever. It's easy. It's like kind of more sane, at least to me, to like kind of just like kind of have a template that works. We know it works, and we're just kind of swapping the constituents, like the ship of Theseus, whatever. And for now, we're just kind of taking the policy and we're just returning it. Okay, so flip policy horizontally, right? And then like we replace all this stuff with our nice thing right there, and then we do the same exact thing for this one. Okay, now I'm just returning P just to make sure it compiles. One error, cannot find name cell. Okay, let's import it. No problem at all. Export enum cell, so it is exported. And let's make sure that that works again. Good, it compiles. Get status. I'm just gonna do a quick get add just to save everything. Okay, so we have to do policy horizontally, right? I think that it is time now to to do like a clone for policy. So let's actually like kind of like we or do I need a clone? I mean, this is just like the canonical example of reversing a string, right? We just reverse the entries in policy? Is that not it? Okay, let's open up policy actually. Okay. Let me just snag that real quick. Okay, right? Let flipped, this word right here, flipped moves and probabilities equals, and its type of course is that. Equals a new list, right? And now we iterate over the old ones for no, I think I don't know, I'm just more comfortable if we actually clone the policy. If we have a clone for policy. And you have to recursively clone move too, because policies have moves, right? So let's just add the clones first for now. Kind of like that. What? Boom. Okay, so how do you clone a move, right? We just return new move. This dot is for P1, and this dot column index and that is it. That is move. That is now we have now implemented clone for move. Good. That is quite easy. Nothing hard with that. Oh, sorry. Capital N to go there. Now clone game state. That was just a reference. So clone policy. Okay. So then let this thing right here. Let's copy that. Let copy move and probabilities equals a new thing, and then for just a for loop, and then return return new policy using this thing right here, just like that. Okay, let's iterate over it, right? Oops. Let move and prob of this dot, what do you call that? Move and probabilities. I should have said probs. I remember I didn't want to spell out moves and probabilities. Such a hassle. Moves and probabilities. So for each move and prob of our move and probabilities, what we have to do is we have to do copy moves and dot push. Okay, let's just do break by break. Let move copy move equal move and prob 0 dot clone push. Or you can just do it right here, right? And it's that, what? And then for this one, it would just be a move and prob of 1, right? Prob, and a number is a primitive thing. There's no point cloning it. Just that, right? Does this make sense? So to clone a policy, what we're doing is we're the same backing data structure, the moves and probs. We're kind of instantiating a new list, right? And then each of the elements in our list, we have to deep copy them. So then this whole move and prob stuff, we need to kind of create a new list, a new sublist. Again, this is a lol, a list of lists, right? Or a list of tuples, a lot, LOT, a list of tuple, a list of a pair, right? A list, we have a list, right? A list of all the moves and probabilities, and it's a list specifically of another list, and the sublist has 2 elements, a size 2 list, sublist, nested list, where the nestee, the element that is in the outer list, is its own list with the 2 elements moving a number, right? So that list also has to be a new list, because we don't want to I don't know, just in terms of good principles, it feels like that should be deep copied too. They should not point, these 2 lists should not point to same, they should point to new objects, a new sublist. So our new sublist we're actually building right here. And that new sublist, again, lots of nesting, has a move object, and that move object should be a deep copy, a new move. Move and prob 0 gets us the same move that we currently have, and we're just going to clone it. And clone uses the new keyword to create a new thing. And move and prob 1 is just a number. Okay, yeah, that's fine. Okay, this looks good. I'm quite pleased with that. Okay, so now we have a clone for policy. So right here, in flip state, what I was going to do here, I remember I try to talk my way out of it, but what I'm going to do here is the same clone. I'm just going to copy that there, and then do that, and then just yoink it right there. And then same thing for here too. Boom. Good, good, good. So now what I'm going to do here, right, is what I can do now is I'm just going to clone the policy here, just to let copy p, or p copy policy equals to p dot clone. Just a nice way of just not touching p at all. From the get-go, we're going to clone it. Okay, that's a good idea. So now what? So we have copied it, right? And now for let me just kind of copy these lines right here. Wait, no, we can do let of. So what we have to do is we have to kind of flip it, right? Is there a helper method to reverse the list? It's a one-liner reverse list. In place. I mean, we're dealing with a copy. So we just do I mean, array 1 is 1, 2, 3. Then reverse is 3, 2, 1. Then array 1, so returns that. Returns its own reference. Same array. So it's destructive. So like we did it in place, so we mutated it. Okay, yeah, great. So what we can do then is copy p, right? And we can do is just copy p dot moves and probabilities dot reverse. We just dot reverse that. Actually, no, that kind of makes me feel uncomfortable. I want to implement it myself. I don't want to use this built-in thing. Let size number equal to copy p dot this thing. I was even talking about this dot length, right? Dot length, and then sorry, -1 int let end number, let end let oops, sorry about that. Let start number equals to 0. Let end standard, very standard 2-pointer approach. Let end number equal to size -1, and then while start is less than end, we swap, and then at the end what we're gonna do is a start plus plus. I remember I once forgot this and I had an infinite loop, and that was really embarrassing. End minus minus, right? And then we have to swap them, right? So let temp, which is the type of the nested thing, which is this, that. Let's just call this temp. Oh, yes, so this one is copy p dot that dot let's just cache the started ones because we're gonna override it, right? So then let's paste that there. Whoops, what am I doing? So let's just take this, right? Go here. So this dot start, right? Now we have to set it to this, but for the end. Like that, right? So the start becomes end. So now both end and start, they both like share the same thing for end. So we've overridden that. So then now we have to like do the same thing for the end, right? End, and that equals temp, right? Because like if we were to do this for start, but then that has already been overridden, so now we just have to take in the temp, right? Just a quite standard standard swap procedure. I know like for numbers you can use a very nice XOR trick without even using a temp variable, which is really cool. But yeah, we have to store the temp reference. Something with Futurama, I don't know. Okay, does this look correct? And what about edge cases? What if it's an empty list? Well, no, the policy has to be non-zero length. The size has to be greater than 0, or else that was a terminal node, and there's no point ever doing this. We only do policies, like policy 1 precondition is like the size of this has to be greater than 0. It has to be at least 1. So if it's 0, then that's negative. I mean, if this were 0, then end would be -1. We never would do it anyways. So this whole loop wouldn't matter. So the size is 1. Let's just say like the other base case. Then start equals end, and then this does not hold true, so we skip it. So this only applies like when we have at least 2 elements. Then start would be 0, and then end would be 1. Okay, so then there's an even and odd case. So if it's even, then we swap it, and then start and end is like 0, 1, and it'll become 1, 0. It overshoots. Okay, and if it's odd, then after, like if it's size 3, then 0 and 2, and then 0 plus plus, 2 minus minus, they both equal 1, and we don't touch the middle element. So okay, good. The odd case checks out too. So evens and odds, so yeah. Okay, good. And we can do induction, we can keep adding starts. So yeah, that looks good, so I can just accept that. So we cloned it, and then we did it in place. In place, we just swapped everything. And then we never actually we only kind of overstamped. We never adjusted the length. The length, everything's pretty. It's just a simple in-place swap, right? Okay, yes, that looks good. While start is less than end, 2-pointer approach. Yep. And then let's delete this. And then now that we did all that stuff, we return the copy P, right? We return that. So this flips the policy horizontally. And again, this we never touch, we never ever touch that. We always kind of clone it. We always have the new thing somewhere, either directly say new, or the clone itself has a new, and then we in place reverse that. And is reversing the same thing? Let me just kind of make sure about that. Okay, I mean, I think so, right? 0, 0, 0, 1. Okay, let's just say that so for a given column, right? For a given column, where would it be reversed? Let's say the 0. This first column has some probability, right? And when we flip it, it becomes at the end. So then yeah, so it basically swaps. Right? This whole thing right here, right, is kind of the same thing. We just have to reverse it. What is at the start, this probability at the start, it ends up at the end. And what's at the end just so happens to end up at the start, right? Let's say that we really want to place here, and we kind of want to place here. Then when we flip it, that means we really want to place there, and then we kind of want to place here. So these two are kind of the complementary pairs that are kind of start and end, and we keep and so forth for all the others, the nested. Okay, yeah, that looks good. Okay, let's make sure this compiles. And then again, it's kind of symmetric, at least for that. I mean, again, this is only for connect 4, this case. If we were to do a rotation, let's say we have let's say we have a go board, if it's n by n, which is a square, right? Then if we were to kind of rotate 90 degrees again, then we'd get rotated 90 or pi over 2. If we do this once, we get a new kind of rotated, and then if we kind of do it again, right? Then we get it rotated pi, or 180 degrees, 90 to 180. So in this case, this whole operation is its own inverse. But I guess for reflections, it would be kind of if you flip out an axis, then an even number of flips, it's its own inverse. But for rotations, I believe that we cannot just use the you see how we're kind of using its same thing as its own inverse. We're passing the same flip thing for both the transform policy and the inverse policy. Now, in general, I don't think that this holds. This only holds for this connect 4 flipping case. It won't hold for rotations. But in BumperCoins as well, I think it's its own inverse, which is really nice because they're both flips. They were both rotations, and they're not reflection. I mean, they're both reflections, not rotations. Again, go board invariant to rotation and reflection. But for us, it's only invariant to reflections, not rotations, because it's not a square board for both connect 4 and BumperCoins. Okay, so that's pretty good. Now that we have symmetries, let me just make sure that it compiles. And it does not compile. Cannot find name move. Okay, let's import move. yeah. PG, YY, move. I just want to get out and eat some lunch now, so let's just quickly finish that. Clear, TS, wait, what? TSC. Okay. Copy P. Oh, how helpful. Line 57. Yep, copy P. And same for the other one too. And same for that one. Okay, so then copy P is the copy of the policy. Then we get its size, and we in place reverse all the elements by the two-pointer approach. Temp copy P, then we kind of take that thing at start, we cache it in our temp, and then we stomp it out with the end. And then from the end, now that we've done end to start, we have to kind of do start to end. And then that's where this temp comes in, because we stomped over it. So we kind of restore that, and then we adjust the pointers, and then that's it. And then we just, at the end, after everything's done in place, we just return copy P, which is the clone of this, but it's been reversed. Okay, that's good. I think that's all. Okay, great. Get status, get add all, get status, get log, and then let's just should I actually use it in our create node? Let's see. Let me just briefly use. Actually, yeah, I'll just commit this and then peace off. Get status, or no, wait, what am I doing? Yeah, get status, get log, copy it like kind of initial tentative. Get commit initial initial. Let's call this introduction of symmetry object. Untest, or just initial introduction of symmetry object. Initial, let's just put this weasel word tentative. Initial introduction, or slash sketch maybe. Sketch of new symmetry object. Get status. Get push. Alright, yeah, I'm gonna head out and eat some lunch now. So that's all for now. Let me just make sure that I just like to refresh this and then make sure that it's pushed. So in case my laptop gets stolen, like it'll still be here. Clone. So we did a clone for move, which is returns a new move. The keyword is new for a new object, great. And then these are both, this is a Boolean, that's a number, this is both primitive. There's no need to deep clone them. And clone for policy. We just kind of like take the move and probs, and then we kind of, again, new list, important, and then like a new size 2 list where it's move and prob of 0, which is the move, but then that's a pointer to move, so we have to deep clone it, and then move and prob 1, which is a number, so there's no need to, it's primitive, no need to yeah, it's just number 1. And then that's the move and the probability. So we copy the new cloned move and then the probability, which is a new, it's its own thing. The same like binary zeros and ones get kind of like the same zeros and ones gets kind of copied over, and that's fun. And then symmetry.ts, crucial thing, we have like this like goes from state to state, policy to policy, and then the reverse of that, from the new policy, the new transform policy back to the original one. It just so happens that like for BumperCoins and the flipped horizontally, the policy, like they're both policy. Like these are, it's its own inverse. Keeps it horizontally. Like we have these like symmetry object, which like takes in like these 3 arrows that have circled, like this one, that one, and the reverse. S to S prime, P to P prime, P prime to P. Those 3 transformations. And then those are just symmetry has these services, like these 3 things that it can do, and then we just kind of pass in the lambdas, and then it just kind of does it on it. It just kind of does that. That's it. This feels a bit like boilerplate code, Like maybe just these are enough and then like we kind of apply it, but I don't know, it just kind of feels nice to write it all out and goes from S to S prime, P to P prime, P prime to P. And then I have now created like this identity transformation symmetry just for fun, like just game state, we just clone it, policy, clone it, policy, clone it. That's it. It's a no-op. It's just like itself. It's the identity matrix. And flip state horizontally, I already mentioned that, just like flipping everything about the vertical axis, where like we do R and then like this thing, which is like the size -1 minus that. And if you look at this size -1, right, it gets reflected here, right? So like whenever like start plus plus, right, and minus minus, that's the same thing. Because if we were to increase this size by 1, right, that means we're minusing, so minus gets distributed around the parentheses. Like if we decrement this by 1, that means this one we get increased by 1, right? Because the negative sign distributes across the parentheses. There you go. So like that kind of like shows this nature of this thing right here. Like we don't have to do start less than end. We can just do start less than mid, and then we can like use this function to generate our end, right? Because this complement function. But okay, I mean, yeah, that's it. And then like, again, like when C is 0, then like end becomes size -1. So like this function right here, this formula right here kind of, it shows that. So that's pretty cool. Okay, I think I'm going over very elementary stuff too much. Yeah, I guess this all makes sense. Horizontally, policy, like these are both the swap functions, and then we build up past these lambdas, these functions as our function inputs, our function arguments, and we have now instantiated. I guess I should delete these 3 deadlines, whatever. And we have now created symmetries, which we're exporting. So in the future, when I'm doing like the Monte Carlo tree search, I already talked about this in the beginning. So like next time, at least in our tree search, I'm going to actually like use these exported symmetries. Okay, that looks pretty nice. Nice and easy sub 100 line code. Looks neat and tidy. So I will call it a day, or at least a stream. Yeah, probably a day for now, so I'm done. So yep, that is it.